Hey, good afternoon, everyone. This session is going to be in English. So, my name is Amit, and I'm joined by Mohit. We are part of Dream11, and we are here to talk about. Okay, we are here. We are excited to talk about the challenges that we faced in scaling Spark at Dream11. Dream11 being the largest fantasy sports platform in the world. So, we'll talk about how one of the key challenges that we faced was scaling Spark, which meant mastering a lot of massive scale shuffle operations. And while doing that, we evolved our architecture to first start using remote shuffle service, which then like evolved to us using Apache Caliban. So during this journey, we did a lot of trial and errors. Then we had some pain points that we uncovered, and then there were some attempts that we'll cover today. We'll also talk about some other optimizations that we have done apart from Caliban, uh, with some LLMs and auto tuning of Spark jobs. So So talking about Dream11, Dream11 operates just in India at this point, and we have a user base of about 260 million users. We operate at a scale of about 10 petabytes. Our peak transactions are around 43 million per day, and we also process 500 million real-time events in a day. On the compute side, we do provision around thousands of Spark clusters every day, and which contribute to us running around 5,000 workflows in a day. So during major sporting events, we also serve a peak concurrency of about 15 million users on the app who like play. So most of the user base is around cricket because cricket is a popular sport in India. So with this scale, we do end up with a lot of challenges around compute and data. We'll talk about that. So especially around Spark, we like the biggest challenge that we initially faced, like this is a journey over the last 2 years, was like not having a lot of insights on the workload size or type, which led to a lot of tenants overstepping on each other and like leading to resource crunch and also underutilization of CPU resources. We then like when we started using spot instances to have lesser cost footprint, we we faced issues around when there was a like a spot interruption, a lot of spill data was lost, or a lot of the shuffle data was lost, and we had to retrigger the job again. During slow cluster creation times, a lot of SLA was missed, and that led to downstream impact. The major problem that we have faced is around shuffle, so which like is around the network throughput, network throttling, and the disks which are not able to keep up with the scale of shuffles that we're operating at. So to tackle all of this, we leaned on to our in-house ML platform. So Darwin is the ML platform that we have built over the last 2-3 years. So this is a one of a kind platform which gives you Ray and Spark out of the box natively. So you can do massive data processing as well as ML training in the same cluster without having to switch anything. So it has its own complexity because we have to run Spark on Ray, which like leads to other challenges that we have been solving over the last 2 years. So this is the compute layer. Data connectors, we have connectors which connect to Redshift, Iceberg, MySQL. Caliban is something that we have integrated recently. And then like these abstractions are provided to our users, which is the workflow, which is the orchestration piece, and the workspace, which is like notebooks for you to run your jobs or like code in isolation. So we'll cover how we have looked at the journey of integrating Shuffle service in ML platform. This is where we carried out most of our experiments and like a lot of integration was done on Darwin. Mohit will cover the rest.
Hello all, ni hao. Uh, as Amit rightly mentioned, that the scale that we deal at is massive, and the amount of shuffles that we execute every day is pretty huge. We came up with a lot of headaches, and our first serious attempt towards solving this problem was using the AWS FSX lecture. So it's more like a file system that AWS provides as a enterprise service, and we wrote our custom implementation on top of it. The idea was pretty straightforward. Just get every single shuffle data out of the lifecycle of executor and put it onto the disk that AWS FSX provides. This actually should have helped us very well in terms of using Spot And when I say using spot, it means that using it much more aggressively, so that even if the node goes down, the compute is separated. Uh, yeah. So this was our first set of architecture that we had built. If you look at what Amit had already explained regarding the Darwin's architecture, there's a compute layer which talks to the EKS control plane to execute or orchestrate different clusters on the EKS fleet that we have. We mount FSX onto each of these worker nodes and ensure that the FSX is available to most of the workers that we have, which are executing the shuffle workloads. This helped us use Spot very aggressively, as I already mentioned. This also ensured that failure of Spot nodes and the downstream stages where we are connecting to most of the databases which are available, like Iceberg, Redshift, Delta Lake, SQL. All of them are available and they are more resilient as what it used to be. We assume that this was the last and foremost implementation that we'll have, but it did come up with a lot of headaches that I'm going to talk about. First and foremost, FSX being very expensive on cost. So as we went ahead with using FSX, initially it was pretty smooth. As we moved more and more data workload over it, we realized that the cost shoot up and it was massive. As we have more and more heavy jobs running, even the throughput limit kicks in, and we had a lot of bottlenecks around the network, especially during concurrent heavy shuffle jobs, which became a lot of more painful to handle. As we were having a lot of FSX, and each of the starting point of FSX, it requires a slow startup time. So additionally, the overhead to ensure that the FSX is up all the time, there's a certain amount of FSX keep running throughout the journey of a job. It became pretty overwhelming. And lastly, since we have a diverse kind of job, some are pretty small, which executes few MBs of data, to something which deals with petabytes of data. It became very difficult over the period of time to live with one kind of implementation or living with FSX shuffle, and that's where Celebon entered our ecosystem for the first time. So as a fellow colleague at Ant already mentioned, that Celebon is an expert in terms of managing shuffle, so we did use it at a very good scale. As it is purposely built for remote shuffle service, it scales well. We did a lot of custom implementations so that we can execute the operations per tenant. We had a lot of fault tolerant being injected into the system because of the data replication that it provides. And because it was very easy to deploy on Kubernetes, it became like a cakewalk for us to manage the shuffles at that point of time. As now you look at the architecture, it became more and more complex. Everything starts with something like a Spark gateway that we had provided. If you see over there, every single user from different teams and different tenants comes over this gateway with a particular execution or particular kind of job that they want to run at. This goes through the Darwin layers, where we have a lot of orchestration and scheduling of jobs being taken care at. And if you see the last box very carefully, and you notice that there's a separate fleet for Spark workers and a separate fleet for Celebon workers, ensuring that the compute node and the shuffle node are separated and decoupled, ensuring that we have much more resilient to Spot node losses and even executor losses in case of Spark. As you see below, there are Spark and Ray operators. We are primarily using Ray DP to run Spark jobs, and some jobs which run on top of Spark, plain vanilla Spark operator. And this ensures that we are able to scale it up very smoothly. And as the load goes down, we are able to handle that as well without having a lot of operational overhead. In terms of Celebon, we are using KDA, which actually brings us a lot of flexibility in terms of keeping the disk higher and lower based on the load needs. Additionally, there are a lot of other operators that we've added, which includes Datadog operators to manage the monitoring. There are a lot of operators which ensures that all the AI workloads are also managing. So, as I already mentioned, Celebon did come up with a lot of boons for us. To start with something like infra management, we ensure that we are mounting NVMe disk, which are a specific kind of disk or SSD based disk, to make sure that the shuffles are blazing fast. We also ensure that the jobs that we are running, everything related to that job spaces around the single zone or a single rack of AWS, to ensure that there are no network chatters or the cost that we incur while network transfers across different zones. For every single job, the configuration of Spark used to be pretty same for most of the diversity that we have, and this was one of the problems that we used to incur earlier. We ensured that there's an engine that ensures that smooth or based on the load, your Spark configurations are optimized. We also incorporated vlogs and gluten to ensure that there's a vectorized execution which gives us a boosting performance. Additionally, as I rightly already mentioned, that KEDA helped us to have this flexibility of keeping the disk higher or lower based on the demands. So we had a lot of spiky traffic when it comes to scale. Within about 5 minutes, we get about 1 to 15 million RPM on the users facing APIs, and that also reflects back on the things happening behind the scenes. We also ensure that we have multi-tenant setup for Celebon, so that there's no issues of two use cases intervening with each other. And last but not the least, over the period of time, we know that how our workload triggers, how our traffic increases or decreases over the period of time, and we ensure that we are scaling much more regularly and in advance to ensure that there's no loss in terms of startup time specifically. To summarize the base set of optimizations that we have done, as I said, there's fine tuning of different configuration before triggering a Spark job and before stages of Spark job. We started off with something as a default that Spark gives of 200, then move for shuffle partitions to 2000, and later on auto-tuned it on every single stage. As I said, zone awareness ensured that there's no network chatter issues over the period of time, making it far more better utilized. Executor, we moved over the period of time towards bigger executors and fewer executors when compared to tiny and more number of executors. This reduced a lot of network overhead that was there while transferring data from one pod to another. Additionally, all the scaling was being done preempted in most of the cases, or predictive in most of the cases. And last but not the least, we had disk caching enabled on top of NVMe nodes, which acted as a catalyst for increasing the shuffle operations at speed. Next, Amit will cover on the AI part.
So we also built our parallel systems to, because Spark like execution performance boost is not enough. We also have to improve the operability of our jobs. So there are two agents that have been deployed alongside all our jobs. One is about debugging what has gone wrong in a job, and then also helping with fixes. So this is one of the snapshot of the jobs that is running, which looks at all the logs that executors have given and figures out what has gone wrong and gives recommendations on what could be improved in the configuration of your Spark jobs or something else in terms of infra configurations. So like that was the initial phase of this. Now it has evolved to doing a lot of autonomous action taking as well. So as we have gathered data around what kind of configurations work the best, we also start applying that once the job goes down or job fails, and then like automatically the job recovers with the new configurations that have been figured out. There is another agent which is about auto tuning of jobs. This looks at your historical data on how the jobs have been performing, tied with our patterns on the app, and how the jobs are getting triggered over the past data. And then this helps us in automating or like auto tuning our jobs, where like a user does not have to specify the configuration of Spark, and let the system, like with the initial configuration, it is able to figure out all of those things on their own. And it helps in giving us better SLAs, lower cost footprint, and also helps in resolving a lot of errors. Earlier the journey was, if something fails, there was a manual triage of what went wrong, and it used to take up a lot of time of the entire team. a lot of this has been automated now, and it helps us giving a good boost of operating new workloads, varied workloads, and like increasing the volume of what the data team can handle. So yeah, that's like the journey that we have taken with AI as a part of the job orchestration piece. So overall, with all these systems that have we have built, Caliban, the auto recovery mechanisms, our stability increments have gone drastically up. Like because the spiky load, it was difficult to predict what has gone wrong. So we have had a job success rate go from 71% to 94%, and then with some optimizations on the AI side, it has gone to 99% very recently. The SLAs also have gone up. SLAs also, the agreements have, like, we have been able to meet all of them. Cost optimizations, we have been like, because spot interruption was a major issue that we faced earlier, with a lot of resilience built into the architecture, with Caliban, like we have been able to do a lot of cost optimizations, and we are like doing it at a 50% cheaper rate than what it was earlier. As Mohit mentioned, rack aware scheduling has also helped us with reducing some cost and the overheads that we had on the network side. So that also helps us reduce cost and give us more efficiency to our users, and like ensure that the platform runs smoothly. Okay, so final words. I think Caliban's architecture perfectly suited our multi-tenant needs. Like we have been able to give the guarantees that every tenant needs to our platform. The Kubernetes native deployment have simplified operations. We have been an like early adopter of Kubernetes, so for us latching onto any new technology which is Kubernetes native was like easier job. Auto scaling also has helped us provide cost efficiency without a lot of performance compromise. In fact, the performance has also gone up. And choices around a lot of experimentation that we did around spot to on demand switching, rack aware deployments, dynamic configuration tuning were like in their aspect small, but over the large scale that we operate, like they were having huge impact. And then like the AI integration within our systems have helped us with like figuring out the right optimization strategy for all the workloads, and like it has helped us tune the jobs for better performance. On the next journey, we are trying to integrate catalog as well as part of the smart schema management, and then workspace powered code suggestions to boost performance. Like this is where like the developers themselves can write better jobs, and like help us fix the issues at the top of the funnel. Yep, that's all from our side. We are hiring in India if anybody wants to come to India.